check out this problem. It looks a little bit different than the ones that you have seen previously. Now, what we would do on the other ones is we would start with exponential form and convert it into logarithmic form. And we can totally do that here. And I'm actually going to work it out that way in just a second. But there's another cool trick that I would like to think is very obvious that we could do here. And we'll do that one last. So let's do what we've been doing. Let's just convert this into logarithmic form. So we have log base 2, it's this 2 right here, of this entire number, 2 to the 12th in all its disgustingness. And that is equal to 2x. And this looks a little cluttered and it might seem a little weird, but it's going to make sense when I word it this way. 2 to what power is 2 to the 12th? Okay, what? Well, 2 to some power is 2 to the 12th. Then that power had better be 12. Okay? Now, there's another way of looking at it that involves some properties of logarithms that are beyond the scope of this lesson. In another lesson someday, you will probably encounter the fact that this 12 can move down and become a coefficient, and it is a lovely thing to do. We're not going to do that right now. It's great. It'll knock your socks off, if you're wearing socks. There we go. But basically, 2 to what power gives me 2 to the 12? It would be 12. So then we would divide by 2, and we would get 6. Now, if you were looking at this from the very beginning and saying, that's just 6 because I see it, then you're right. Because what you also could do, and let's rewrite the problem, you don't have to, but what I could do is look at this and say, well, I have the same base, 2 to the 2x equals 2 to the 12, so I'm going to mark out the 2's. Now, the reason you can do that involves a little bit of properties of logarithms and pre-calculus related topics, and so I'm going to do it without really showing the work behind why it is legal to do that, but you're left with 2x equals 12, which gives you 6, which was no surprise because this one was fairly obvious. Now, the next one may not be, so we're going to work our way towards getting ones that are obvious. So we're going to call this one obvious, and we're not going to call the next one obvious. We're going to call it slightly not so obvious. 4 to the 3x equals 2 to the 12. Now, if you wanted to, you could put this in logarithmic form as well, like we just did on the other one, but I'm not. So I'm going to go about this one a little different way. If you are following along with the notes that I have provided, if you're one of my students and you're doing that, you can flip the notes over and you're going to see a lovely chart that looks incredibly overwhelming, and it's a list of powers. It's 2 to the 1st all the way to 2 to the 10th, and then 10 to the 1st all the way to 10 to the 10th. Those should be obvious because you just put zeros on the end of the number, right? But what we're going to do is try to identify what the lowest common root base would be, not root, common base would be. And so this one's fairly obvious. In this case, like if you flip the paper over, you'd see 2 to the 1, 2 to the 2 equals 4. So 2 to the 1 is 2, no surprises there. 2 to the 2 is 4. So what I'm really going to do is say, you know what, I don't want this to be a 4, I want it to be a 2. Why do I want it to be a 2? Well, because this one's a 2, and I want them to be the same. So again, we're aiming for this right here. We're aiming for this idea where these bases were the same, and we could, for reasons that I have not explained, just simply mark them out and set the exponents equal to each other. So that's what we're aiming for. And so we're going to do that. We're going to say, well, 4 is really 2 squared. So let's take this 4 and we're going to make it 2 squared. Sounds good to me. And that's equal to 2 to the 12. Well, that's wrong because we've left something off. We already had an exponent of 3x. So we're going to multiply by that. Why do you multiply? Because that's how the properties of exponents tell us to do things. So we'll do that. So at this point, we do have the same base. We have 2 here, 2 here. We'll mark them out. And we're going to have 2 times 3x. We'll go ahead and call that 6x. And that's equal to 12. We'll divide by 6. Why am I showing that work when we could just do it in our head? And we get 2. Okay? Hope we're all right. We're going to take this idea and expound on it a little bit more with some bases that get a little bit larger than 2 and may not be so obvious. So let's go to the next problem. Well, the next one doesn't have a base that's larger than 2, does it? For 2 to the 2x minus 1 equals 128. Now, we have done ones like this before where we would start by putting it in logarithmic form. And you totally could after you move this 4. Right? So this 4 is in the way. So again, if you're going to start doing it the way we had done it previously, then you could write log base what? And then you'd be like, I don't know. Well, you got to move the 4 first. Okay, so that's what we're going to do. Let's get that log out of the way. We are going to divide by 4 on both sides. And we better go. All right, 2 to the 2x minus 1 is equal to, well, 128 divided by 4. That is 32. And so now we have something that is truly in logarithmic form, exponential form, which can very easily go into logarithmic form. This looks like the problems we started with, but I'm going to go about it a little bit differently. Since we have this wonderful chart on the back of our paper, I'll be able to look and try to find a 32 somewhere, and it won't be hard to find. There's your 32 right there. And so here it is. 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8. Wow, I paused way too long on that. 2 to the 4 is 16. 2 to the 5 is 32. My mind was elsewhere. I was actually thinking of, instead of doing 2 to the 3rd in my head, which should be automatic for me, what I was doing was I was comparing it to the way we've done this previously, when we would say, oh, well, the number's in between this and this. Well, in this case, the number's not between anything. It is one of those things, right? So 32 is 2 to the 5th. So I'm going to take 32 away and put 2 to the 5th in its place. I'm not taking it away in a subtraction sense. I'm just substituting an equivalent value. So we have 2 to the 2x minus 1. And now we'll do this magical thing where we can mark out the 2's. They're not always 2's, I promise. 2x minus, well, the next one's not, is equal to 5. And we're going to solve it. And you can probably do this one in your head, but you're going to add 1 to both sides. Gives you 6. Divide by 2. It's going to give you 3. Okay? By the way, no rounding in this, no craziness. You plug that in, it verifies, it works. So let's do one more in this video. And it's going to be a little bit trickier. It is 125 to the x minus 1. And that is equal to 5 to the x. Now, we can't use logarithmic form on this in the way we've been doing it. We could finagle our way around it, but we're not going to. What I am going to do is try to get the same base on both sides of the equal sign. And let's just go for the obvious. It's not going to be 2, right? It's going to be 5. I'd like to think it's obvious. It's not always the lowest number, but here's what I do notice. If you flip the paper over, you'll see 5 to the 1 is 5. Got that. 5 squared is 25. 5 to the 3rd is 125, and there's a longer list, but we have everything we need just with this abbreviated list here. So 125 is 5 cubed. So instead of 125, I'm going to write 5 cubed. So let's write 5 cubed. So 5 cubed. That's great. Equals 5 to the x. You might stop here and say x equals 3. Haha, wait, no. Because there was an exponent here that we never dealt with, and so we will put it in there. And we're going to multiply by the new exponent that we got. Properties of exponents. Okay, do the pre-cal thing that we don't explain. Let's go ahead and distribute 3 times x, 3 times negative 1. That's going to give me x. And we're going to solve it. It will be a decimal. It won't kill us. Let's subtract 3x from both sides. Get our variables on the same side. Cancel those. We'll have negative 3 equals negative 2x. That does not look like an x. It looks like, well, a Greek letter, lambda. In case you wanted to know what a lambda looked like. I mean, you could go out in a sheep pasture and find out what a lambda looks like, right? Ha! That was not funny. Okay, lambda, 1.5. There we go, that's it. I hate to end this video with such a bad joke, but there it was.